Okay, thanks. Yeah, I'm going to talk about multidimensional virtual values and second-degree price discrimination. It's going to be about multidimensional mechanism design and a framework that we have to prove optimality of mechanisms. And at this point in the workshop, I hope I don't need to try hard to convince you that multidimensional mechanism design is hard. It's complex, both in terms of the structure of the optimal mechanisms that we see, and also analytically and computationally. Fortunately, also, we saw an excellent sample of the approaches that you can take to tackle this complexity during this workshop. So, for example, we saw algorithms, approximation algorithms, like what Matt and Young talked about. We saw characterizations, like what Christos talked about, and also there is another paper in the econ literature by Roshan Chonet. These characterizations are very general and very strong, since that they can, if you have a certificate of optimality, you can use it to prove the optimality of your mechanism in very general settings, but we don't have general methods to come up with these certificates. There is alternative models, how can we change the model a little bit to get more tractability from it, like what Gabe talked about and when he talked about robustness. I'm going to stick to our favorite Bayesian setting and present methods that we have to prove optimality of mechanisms or simple mechanisms. So again, we also discussed this, that very often the mechanisms that our theory predict to be optimal are not the mechanisms that we see in practice that are run. And it's good to have general methodologies that you can go look at your favorite market and your favorite mechanism and see, try to explain why this mechanism is actually the mechanism that we see by proving it is optimal. So in some sense, we try to rationalize mechanisms that we observe out there in the world. So let me give you now a sampling of what kind of simple mechanisms I'm talking about by some examples. The first one is what we all know, the single item monopolist seller who is facing a single agent with unknown values, and Meyerson and others showed that a simple mechanism, which is just to post a price for the item, maximizing the expected revenue of that price, is the optimal mechanism among the class of all mechanisms that could involve randomization, negotiation, and everything else. Now let me make this example one step more complicated by saying that let's say we have a single item to sell, but there are two ways to deliver it. So let's say that we're thinking of an online retailer like Amazon. You're buying something online. There are two options to deliver it. Either Amazon can use a express shipping method to deliver this item to you as fast as possible, or use a standard delivery method that's going to take longer. And let's say that the buyer has some value V for immediate delivery and some V times theta, where this theta is the discount factor for the delayed delivery. Let's just assume that this theta is less than 1, meaning that the buyer wants it as soon as possible. And also, let's say that there is no cost for either of these two shipping methods. Now we want to know what mechanism is optimal in this setting. And Stokey first showed that if theta is known, if the seller exactly knows what discount factor is, and the only unknown is the value for immediate delivery, then you might as well just post a price for immediate delivery and never offer the buyer the delayed delivery, which makes sense, right? Because we know theta, we know that the buyer always likes immediate delivery more than the delayed delivery. So if you want to maybe maximize revenue, we should maximize surplus. So give the buyer the item or the option that he likes more. Rather surprisingly, we know that this doesn't hold in general. So if the value and this discount factor are coming jointly from some distribution, then Solis was the first one who noticed that you can do more sophisticated mechanisms. So for example, you can offer lotteries and improve your revenue. And the idea here is that now by offering a more sophisticated menu of options, you can partition the buyers based on the preferences. So some buyers will buy immediate delivery, some buyers will buy lottery, some buyers will buy delayed delivery, and essentially price discriminate. So offer people different prices and not worry about these prices interfering with each other too much. I'm going to stick with the task of proving that the simple mechanism we talked about, which was only offering a price for immediate delivery, is optimal. And in particular, we're going to show that if v and theta are positively correlated, I'm going to make this precise later, then the optimal mechanism is to just offer a price for immediate delivery. Again, I'm going to make this formal later, but for now, notice that if v and theta, for example, are independent, we can show that the optimal mechanism is to only offer the immediate delivery. Let's see example number 3. It is the case that you're selling 2 items. Now, the buyer has some value for the bundle, some value times theta 1 for getting only item 1, and v times some other theta 2 for getting only item 2. And again, all I'm assuming so far is that theta 1 and theta 2 are less than 1, meaning that there is free disposal. The buyer only wants more stuff. And there's no cost. Then you can, again, go through the same argument and maybe at first conjecture that since bundle is a favorite outcome for the buyer, maybe you should only sell that. We have seen many examples in this workshop that this is not true, not surprisingly anymore. And we can do more sophisticated stuff. But again, in this talk, we are going to see that if both of these parameters are positively correlated with the value for the bundle, then you just post a price for the grand bundle of items. Good. So there are 3 examples. They're kind of similar, kind of different. Let's see first that they can be unified in a single model. So these 3 examples, single item, we wanted to show the posted price is optimal. Marcin did that already. The example 2 was 2-way to deliver. We wanted to show that posted price for immediate delivery is optimal. Example number 3 does 2 items, 3 outcomes, and posted price for the bundle is optimal. So this is the model. This is all the model that we're going to use today, is that there is n outcomes. Buyer has value vi for outcome I. This profile of values is going to be coming from some joint distribution. And there is a 0 outcome for which the buyer has no value. And the utility of the buyer is a value for the outcome that the mechanism chooses minus the payment. So let's see that we can fit all these 3 examples in this model. In example number 1, there was only 1 outcome, that the buyer gets the item. There was 1 value that was coming from a distribution. In the second example, there were 2 ways to deliver. There is a v for immediate delivery, a value for delayed delivery. So there are 2 outcomes. In the example number 3, there were 3 outcomes. Do you get the bundle? Do you get item 1 only? Do you get item 2 only? Good. And the mechanism, as we have seen before, is a menu of lotteries and prices. So a lottery is just a distribution over these n outcomes and the 0 outcome, and is assigned a price. And the favorite mechanism that you want to prove optimal, this simple mechanism that I'm talking about, posts a single price for the favorite outcome. So this mechanism becomes posted pricing for a single item because the favorite outcome among 1 outcomes is that the buyer gets the item. If I'm talking about this case where the 2 outcomes were delayed and immediate delivery, the favorite outcome was again getting immediately the outcome, the item. And in the case of 2 items where there were 3 outcomes, the favorite outcome was again the bundle of items. So you just post a price for the bundle of items. So if I manage to prove this theorem, we have proved all these 3 results.
By favorite, you mean favorite ignoring prices?
Yes. So the one that maximizes VI. Good. So this is the outline of the talk. This is also our contributions in this paper. First of all, I'm going to describe to you what are these conditions that I talked about that imply optimality of pricing, posting a price for a favorite outcome, and then talk in more detail about the methodology that we have and the proof technique. And the nice thing, yes?
Favorite is the coordinate that is highest is always the same in the throughout the distribution.
Let's say for now that we know which outcome is the favorite. In my examples, that was true. One of the outcomes was always the favorite. Everything extends. We can talk about it later, but for this talk, let's just assume that it is known which one is favorite.
Favorites, sorry?
Yes, it is uniquely known as favorite. Good. No, actually not unique, but it's favorite. Okay, good. So this methodology that I keep talking about is just generalizing the idea of designing virtual value function for multidimensional settings, and as a bonus of extending such a well-known methodology to multi-agent settings, we can say even stuff about multi-agent, multi-parameter optimal mechanisms. So we can compare the revenue from different agents too. Okay, good. So for the rest, I'm going to do the first task first, which is to talk about these conditions and what they are. Okay, so here is the picture that I'm going to keep drawing. So this is just a possible pairs of values that the agent can have for the items. And again, as we said, let's say that I'm selling a high quality and a low quality item. So we know that the agent always likes the high quality item at least more than the low quality item. So we are in the lower triangle. If you want a concrete example, keep thinking about immediate and delayed delivery. But in general, I'm going to talk about high and low quality. Good, so any point here is just a pair of values for these two outcomes. I'm going to start with discussing a class of instances which I call the perfectly correlated class. And what does that mean? It means that, let's say we know types are lying on a given curve. So we have a curve, and we know that all possible types are on this curve. What can we say about this example? Let me first formalize how we explain such an example, how we represent it. So I'm going to have to talk about what the curve is and where on the curve we are. So let me have a distribution that tells us where on the curve a type is, and we have the curve too. So here are the two.
It's a monotonic?
Not now. I'm just not going to assume that for now. But in the conditions of the theorem, it's going to show up. Okay, so let's say that we have a distribution fh, which is the marginal distribution of the high quality value. So where on the x-axis we lie, this is what distribution fh tells us. In addition, to represent the curve, I'm not going to do what you would think at first. I'm going to instead assume that I have a function theta of v that tells me what the discount factor of a given vh is. So given the discount factor, I can indirectly define the value for the low quality item as being v value for the high quality item times the discount factor of this type. Okay, so these two functions are all I need to define an instance in this class. And it's going to become clear in a second why I talk about this theta function, because all my theorems are very nicely expressed in terms of this function, and in some way, this is the right way to look at this problem. So an example is that this theta function, the discount factor function, is just a constant. So we go back to the case that we know exactly what the discount factor is, and my curve is just going to look like a straight ray out of 0 to theta. Okay? Good. Again, my question is only posting a price P for the high quality product the optimal mechanism or not? My main theorem is going to be conditions that implies that this is true. Before seeing the main theorem, let's see another theorem that says when it is not true that this mechanism is optimal. And here's the theorem. If this function theta decreases anywhere, meaning that it's not monotone non-decreasing, then there exists a marginal distribution for the high quality product that makes this instance jointly defined by these two functions, the pricing not optimal for it. Okay, so let's see why this is the case. So let's look at any p at which this theta goes down. So at this p, the theta goes down because if you look at the angle of the line from 0 to p, it went down as my value increased. So I came up with a pair of values for which the theta, the discount factor of the high type, is lower than the discount factor of the low type. So let's look at any such p where theta goes down. And I'm going to, first of all, pick the distribution on marginal distribution on high values such that if I were going to post a price only for the high quality product, p would have been the best price. So pick any distribution that you like that makes p the best price if you were going to only post a price. That's all I have to do with f. Now I just want to care about the curve and how it looks like. And what we are going to show is that there is another mechanism that improves revenue compared to just only posting a price p for the favorite outcome. And that is simply post a price p for the high quality product. Also, post another price for the low quality product. What is that price? The price is how much this type would have paid for the low quality product minus a tiny discount, minus a epsilon. Okay, so now let's see what's going to happen. I'm going to argue that, I'm going to claim that this marginal change improves revenue, therefore showing that no posted pricing mechanism could have been optimal. So let's see what happens as the result of this change. as a result of this change, the type space is going to be partitioned into 3 sets. One set of types who don't buy anything, one set of types who would have bought the high-quality product if the only offer was P, and now they're still buying the high-quality product, and some set of types who are now buying the low-quality product. So as a result of this change, there is a trade-off in how much my revenue changes in 2 different aspects. One is that there is this little set of types who would have not bought anything if I was going to only offer high quality at price P, and now they're buying the low quality and paying me P times theta. So this is the gain from this change, from that set. So it is how much they pay times what is the probability that they show up. There is, on the other hand, a loss, which is that some types would have paid P, now they're paying this less, the discounted price. This is the expected change in revenue from them, which is what is the change in their payment times the probability that they show up. And the point is that these probabilities depend on how long is this size of this interval of the projected curve on the x-axis. And just trust me, this is just simple algebra, that you can use this property that theta went down at P to show that this marginal benefit is more than the marginal gain, therefore showing that P could not have been optimal. Good. So next I'm going to show my main theorem, which is what are the conditions that do imply posting a price for high quality is optimal, and I'm going to straightly define it for the general class and not only for the perfectly correlated class. All right, so how do I present the general instance? I just need a joint distribution on value for high quality and a discount factor. And these two will define indirectly the value for low quality as the discount factor times the value for high quality. And the main theorem is, so this is the picture again. We have high quality and theta. And the main theorem is this: pricing high quality is optimal if value for high quality and theta are positively correlated. And the marginal distribution F8 is regular. Don't worry too much about the second part. We can relax it. The important thing is this positive correlation of V and theta. So what is this positive correlation? Formally, it is positive correlation in first-order stochastic dominance sense, meaning that let's say that you are given VH, value for high quality. That will imply a conditional distribution for the discount factor, which is a probability that, given VH, what is the probability that your discount factor is below a certain theta? Let's fix theta and increase H, and increase VH. And it says that this is not increasing. So it can only go down as VH goes up, meaning that the probability that is below some threshold goes up as VH goes up, which is some form of positive correlation, right? So it's the standard first-order stochastic dominance. Let's see what it says for our perfectly correlated instance that I described first. So what does it say? So if I have a perfectly correlated instance, meaning that I have a curve, I know very simply what this conditional distribution is. If my curve is below the ray identified by theta, I know that theta is going to be less than this given threshold. So f of theta given Vh is 1 if the curve is below the ray, and 0 otherwise if this curve is above the ray. So now this condition that this conditional distribution is not increasing in VH implies that when I look at my curve and connect a ray from 0 to any theta, the curve must be below the ray before the point of connection and above the ray after the point of connection. So it's kind of curving up, some form of positive correlation. So this is the corollary of the main theorem for perfectly correlated instance, saying that if this theta function is monotone and f is regular, pricing high quality is optimal. Let's compare that to the theorem that we had before, which was when it is not optimal, it was saying that if theta is not monotone, then P is not optimal. So in this case, we have actually a tight characterization of when this is optimal. If you want another story to help you remember this main theorem, think about the high quality product as being the hardcover of a book that we are selling. and the low quality product being the the paperback version of it. And then this theorem says that pricing only the hard copy book is the optimal mechanism if serious readers tend to not judge a book by its cover. Okay, good. So let me just show you some more examples of distribution that satisfy this main condition. The first case, as I said, a special case of positive correlation is independent. So you can have distribution that you draw the theta independently from VH. So for example, let's say that the distribution of high quality product is uniform from 0 to 1. The distribution of theta is uniform from 0.2 to 0.6. This is the picture that you get. This is the domain of the distribution that you get. It's a trapezoid. It's going to keep being a trapezoid as long as you assume that the distribution is uniform over a set. As another example that is not independent, you can pick any of the theta monotone curves that we talked about and distribute the mass equally above it. This is going to be also satisfying our positive correlation property. Why? Let's see why. Let's say we do fix any certain theta, and we see what's the probability that given certain VH, the discount factor falls below it. And we see here that with some positive probability, it fell below it, and it went to 0. So it went down. And if you check it for all thetas, you see that it always goes down, which is satisfying that property. What instance does not satisfy this condition is this instance. So you have a triangle from 0.8 to 1. And if you pick a certain theta, this theta, you'll see that this conditional distribution went from 0 to something positive as I changed from V1 to V2. Why do I care about not allowing this instance in my class? Because this was the first instance that we know that Tanasolis showed that the pricing high quality product is not optimal. So if my theorem is correct, this shouldn't fall in my characterization. Good. So these are the instances. The instances I talked about are all, for simplicity, uniform distributions over some set, where all we cared about was the shape of the domain. But in general, we don't assume anything specifically about the domain, but it's only a condition on correlation. Good. Now for the rest of the talk, I'm going to talk about this proof methodology that I mentioned. Well, before that, these are the main theorems again. So this positive correlation means that only selling the high quality product is optimal. It extends very easily to multi-agent settings. So if each of the distribution of each of the agents satisfy this correlation property, your multi-agent optimal mechanism is just going to be ignoring low quality products and just assuming that you are selling that one high quality product. Then Marcin tells us what the optimal mechanism should look like. So second price we reserve if they're identical, and the more complicated mechanism on the marginal distribution for the high quality product if they're not identical. Good. Now we can talk about the proof technique. To do that, as I said, we're going to extend Marcin's theorem. So let's see what Marcin's theorem was and how it was proven. Marcin showed that there exists a virtual value function, in fact a single virtual value function, that satisfies two important properties that we're going to extend. One, so this is the virtual value function, which I'm going to call phi. One is that the revenue of any mechanism with allocation function x can be represented as its expected virtual surplus, meaning the expected x times phi, where x is the probability that a type V gets the item. Important property number two is that if you look at the allocation of the pricing mechanism, it in fact optimizes this virtual surplus pointwise with even if you relax all the incentive compatibility constraints. So what do I need for this to hold, that the item pricing maximizes x times phi? It's enough that phi is monotone. So if we have such a virtual value function, if I want to optimize x times phi subject to my allocation condition, this is what I get. Below, when phi is negative, I will set x to be as small as possible. When phi is positive, I'm going to set it as big as possible. And then we are done by observing that this is an allocation of a incentive compatible mechanism. It optimizes surplus pointwise and therefore an expectation. And by this property, it optimizes revenue. over all possible allocations. Now we're going to extend this. How are we going to extend it? By extending the integration by parts lemma, which is the key step in Marcin's derivation, which you use to be able to express revenue in terms of x times some form that we don't care about, but just Marcin then called this virtual value function phi, and then rest of the story. So we're going to extend this. And this is how it extends. I don't expect you to understand why, but we're just going to focus on how to use this lemma. So this lemma is an extension of integration by parts plus the envelope theorem to high dimensional settings, and says that for any choice of paths in this space, so pick your two-dimensional or even higher dimensional space and cover it with a certain selection of paths, let's call that alpha, and any mechanism x, you can use a virtual value function that is going to be implied by your choice of paths. Again, don't worry about how exactly, but any choice of paths gives you a virtual value function that satisfies this property, that the revenue of any mechanism is equal to its expected surplus. The difference from here than Marcin's result is that now we have to be careful. This is a vector. This is a two-dimensional allocation. We are going to also get a two-dimensional virtual value function, but the rest is similar. You want to maximize the dot product of these two functions. So let's see some pictures. Let's say that you can pick these straight lines to cover your space, and then it will give you some virtual value function. If you pick other choice of paths to cover the space, it will give you some other virtual value function. Let's see how we can use this. I have not told you what is the dependence of alpha and phi, but let's see how we can use this. Idea number one is what Armstrong did in '96, and said, okay, so let me just pick some alpha. Let me just say I pick straight lines and see what virtual value function I get, and then see if I'm lucky, if I actually can find an allocation, which is an allocation of an incentive-compatible mechanism that pointwise optimizes this. Then I'm done, right? Because I have proven that this mechanism optimizes the surplus pointwise, therefore in expectation, and is incentive-compatible, so we're done. So what we're going to do instead is that we're going to start with the mechanism and try to come up with the best choice of paths that prove the optimality of that mechanism. So we start with the mechanism, we look at its allocation, and then wonder, what kind of virtual value functions do I need to design that this mechanism pointwise optimizes? If I write down those conditions, then I can worry about the choice of paths that give me a virtual value function that does satisfy those conditions. I'm going to go over this methodology in the context of what we talked about to prove the optimality of only pricing the high-quality product. And let's see how we can work it out. So this is the allocation of the mechanism that I want to prove is optimal. So there is some threshold P above which the buyer gets the high-quality product, below which it gets nothing. Now I want to wonder what kind of virtual value functions is optimized pointwise by this allocation. I can write a bunch of conditions, right? So I know that below this threshold, both of the components of my virtual value function should be negative, which is what I need to get a zero allocation, and above which the component of the high-quality product must be positive, and the other component must be less than that. It could be negative, or it could be positive, but it must be less than the one before the high-quality product. If I can come up with this, then my x optimizes x times phi. So I write this down. There's one more step, that now I can actually pin down the virtual value of the high-quality product. Because notice that at this point, I'm assuming that I'm requiring that my virtual value for high quality is going from negative to positive. So it must be 0 on this line. So it must be not a function of what the value for the low quality product is. Let's impose this everywhere. Let's say that the virtual value of the high quality product is not a function of the value for the low quality product. How this helps us is that it lets us extend the result to multi-agent mechanisms, because if two virtual values for high quality products are treated differently based on the low quality, then you cannot just ignore the low quality product and optimize surplus. This lets us find the form of the virtual value for the high quality product Now all you have to do is to plug this into the lemma that we have, which was integration by parts, that tells us what virtual value functions are feasible based on some choice of paths. That turns out to be actually some differential equation. Now that you have one of the components, turns out that differential equation is solvable. It will spit out for you the other component. And now all you have to check is that this condition is satisfied, which is the low quality virtual value is less than the high quality virtual value. And this is exactly where the condition of the distribution comes into play. Okay, so to recap, our theorem is proved with coming up with a choice of paths that imply a virtual value function that satisfies two properties. One was that you can express the revenue of any mechanism in terms of its virtual surplus. Two was that your mechanism optimizes virtual surplus pointwise. Marcin actually does this too. The reason the derivation becomes simpler in this case is that there's only one choice of paths, so you just integrate by parts and then verify whether what you get is incentive compatible or not. There's no choice of paths. In a multidimensional setting, on the other hand, there are many choices of paths, which is good news because we know that there's also many potentially optimal mechanisms. So we can use this choice of paths to come up with the virtual value that proves the optimality of the mechanisms that we are looking for. So you have many virtual value functions that satisfy the first property. You just have to use a property of the mechanism that you want to prove is optimal to come up with the right one that satisfies both of the properties. Okay, so to conclude, we have a set of tools to prove optimality of mechanisms in multi-parameter settings. And we do this by constructing virtual value functions that satisfy these two properties, that revenue is virtual surplus, and our desired allocation optimizes it pointwise. And we reverse engineer the right virtual value form based on the requirements that we impose on it. There are many extensions that I have not discussed. I only talked about two outcomes. This generalizes very easily to the case of many outcomes. We relax regularity, as I said. It's also ironing very similar to what Marcin does. I didn't talk about costs, but you can have costs that you can actually merge with the values, or you shift the values with the given costs, and then the problem becomes similar to assuming no costs. There are different favorite outcomes, as Sergio mentioned, that the theorem easily extends to the case that there could be different favorite outcomes. The form of the mechanism is just going to become post a price for the favorite outcome, and the buyer can pick what outcome he wants. And that's it. Thank you. Yes.
So how does this set of tools prove optimality compare to duality from like what Christian Ramos talked about?
Yeah, so I guess the difference is that theirs is, as I said, a certificate of optimality, so it's an if and only if. Ours is only implying the sufficient conditions, but it's more, I think, more tractable because we have a methodology to coming up with it. And technique-wise, the way they handle it is that we have this revenue in terms of utility and its gradient. They get rid of the gradient and write the problem in terms of utility. We get rid of utility and write it in terms of gradient, which then becomes the allocation function. Yes?
You might be able to have simpler derivations if you redefine the type to be, so you have VH, and then you have an independent variable from VH that determines, that together with H determines VL. And then you relax the problem, so assume that you actually the design
right.
independent variable.
That's right.
And then the solution of the relaxed problem. Is that correct?
Correct. So those are what we call equiquantile curves. So exactly what you said. So it's just come up with some parameter that lets you entangle these two things together, worry about curves, and then put them back together. Exactly. So yeah. Questions?
No more questions. Let's thank Nima again.